So now having told you, okay, what is, how complex these ICs are, servers are, right? And by the way, the desktop microprocessors will be much smaller, but they are also multi-core processors. Okay, if you go look at a desktop processor, it will say some i7 with so many cores, so much of cache memory and so on. That's also actually quite complex, but it's not going to be like 24 cores, 60 cores and all that stuff, right? So then the question really is, how does one even build such a chip? Is it manually? Can you put transistor by transistor, 8 billion transistors, can you put them together manually and build a chip? No, obviously not. So there are a lot of tools that are available, and one way to actually accelerate this whole process of building these circuits, right, digital circuits, is to use hardware description languages like Verilog and so on, which is not part of this course. It will appear in a later course, but in order to understand that, you need to have a sound understanding of logic gates and sequential circuits before that, and that is the sole purpose of this course. Okay, so why should you study this course? It's a fundamental digital logic design course. If you don't get this right, it's very hard to do anything later. Okay, like I said, 8 billion transistors, when I put them together, if they will not work if you have no idea how to get them to work. So that's why you should study this and go bottom up. It's also essential to understand and build microprocessors. If you want to build it, you need to be able to do this. You should do this course, right? It's also very essential to understand how to code in hardware description languages. Now this is a very important fundamental thing that differentiates the hardware from software. Okay, so let us say in software you say x equal to 0, int y equal to 0, I will just say int z equal to x plus y, z equal to x minus y. Okay. Now the way C programs are, you write them and the way they are executed actually in a microprocessor, I will also give you a feel for that, is that these statements are executed sequentially. What does sequentially mean? It means you do z equal to x plus y first, z equal to x minus y next. Okay, so z will get the value of x plus y, then you do a z equal to x minus y, right? So essentially statements are executed one after the other in the order in which you have written them. The compiler may actually, if you choose to compile it with certain options, it might modify some sequences, but essentially the idea is it goes sequentially one after the other. Okay. On the other hand, if I have a circuit, okay, and I have a logic gate, okay, look at this. So essentially what I have done here, I have taken the same inverter and I am giving the output of inverter I0 to I1 and I2. Okay. Now the question is at what point will the output Y1 and Y2 be ready, right? So I0 first of all evaluates, okay, it takes some small amount of time. We'll see, we'll try to define these, how much time it would take and all that stuff later in the course. For now you just assume that if I give an input 0, for the output to go to 1 here, right, maybe I will write that in a different color. If I give an input 0, for the output of I0 to go to 1, because the inverter I told you is just a logical inversion. If you give 0, you will get 1, if you give 1, you will get 0. So for 0 to go to 1, it will take a certain time delay, okay, let us call that delay D1. Once the inverter I1 receives 1, it will take another delay, I will call this D0, D1 for the output Y1 to reach its final value of 0. Now logically Y1 is same as the input because you have just done 2 inversions, right. Now the question is, at what point will the output Y2 be ready, okay. So as soon as I0 evaluates and the output goes to 1, inverter I2 will be acting in parallel with I1, and therefore if you look at the delay here D2, after D2 itself you will have this output go to 0, okay. This is very different from what happens in the case of the sequential logic that we are doing here, okay. So if I were to sort of, I gave you a very simple inverter logic here, but I can map the same logic that you are doing in C, okay. So let's say that you have a block that does addition for you, okay, and you have a block that does subtraction for you, okay. I give X, Y to these two, right. The output of the addition block will be ready, and if I give X and Y to the addition and subtraction block simultaneously, the output of the block will be ready, and let us assume that the delay is the same, right. The output of the block will be ready after the some time delay, right. It will take some delay, but it will be ready after time d. On the other hand, if you were to do this sequentially, you give X and Y to the adder first, then you give X and Y to the subtractor, it would take a delay of 2D for the subtractor output to be ready. So this is the fundamental difference between a software execution and hardware execution. Hardware execution happens concurrently, right, because the logic gate is available, input is available. The moment the input is available, the output will evaluate after a certain delay, right. So in order to sort of code this hardware appropriately in a language like Verilog, you need to understand logic gates and their delays and all that very carefully, very bottom up from a very fundamental standpoint, and that is why it is very essential to do this digital design course as the first course in your curriculum, right. And eventually you need to be able to design state machines to control various systems that you are going to build, okay. You have to build various systems. For that you need to build what is known as a state machine. I will come to what a state machine is in some time. So the course structure, basically the course comprises of 3 modules, okay. We look at the mathematical background, the number system, the representation of signed, unsigned, all these things, right, and how you can do multiplication, addition, subtraction all consistently and in that mathematical framework. Then we look at combinational circuit design, okay, which is basically an inverter is the most elementary combinational block that one can design. And then we will go to sequential circuit design, right. Sequential circuits are very important, but I will not spend too much time on that now. What are the learning objectives of this course? Okay, the learning objectives, first of all, what is a learning objective? It is something that you as a student should be able to do after doing this course, right. So you should be able to design arbitrary combinational logic circuits. For example, I could tell you that you should design an adder, a subtractor, a multiplier, right, or some arbitrary logic I want you to implement, okay. So these are all, for example, I can just tell you, right, you get into your car, after if you observe how the light works or how the automatic lock works, you get into the car, you close the door, you start the car, within 30 seconds, right, or within 30 seconds, all the locks will automatically engage and the car would have been locked. So even if you forget to lock it, right, the car will get, the locks will activate automatically after some time. How does this happen? Internally there is some counter, there is something which is counting up to 30 seconds and then initiating this locking process so that the car can get locked. Similarly the case with your light. You keep the light on, after some time it will go dim and go off automatically in the car, right? So there are a lot of these control systems that you need, and all of that are, you know, built using some sort of combinational circuit and sequential circuit, right? You should be able to use sequential circuits to sequence events in a pipeline. Okay, I'll again come to that later. Now the last statement is sort of putting the first two together. You should be able to design a finite state machine. Okay, finite state machine involves a combinational circuit and a sequential circuit. Okay, now what is a finite state machine? The finite state machine, the simplest example that all of us would have seen is actually your traffic signal counter. So when you go stop at a signal, it goes red. Then there is a counter that starts counting down from either 1 minute or 2 minutes or 3 minutes or something like that, depending on where you are and how the signal has been programmed, right? It will start counting down from 60, 59, 58, 57 and so on, right? It goes down all the way to 0, and we know that when the counter reaches 0, it is going to go green. So around 4 seconds or so, we are ready to start our vehicle, we are ready to, you know, exit from the signal, right? So what is this counter doing? The counter is actually going from one state to another. What is the state? It is going from the state 60 or state 59, right, which represents the number 59 on seconds. After 1 second, it goes to 58, state 58, 57, 56. So if I were to just look at the state machine, right, of your traffic signal counter, it's like this. It starts with 59, 58, 57, it goes all the way to 0, right? And then we know that the signal goes green, right? After this, the signal, what happens after this? It goes to green, okay? And then this enters another, you know, counter of how many seconds it will remain green. Okay, this may remain green for 30 seconds, so 29, right, 28, like that it will go, come back to 0, right, and then let's call this as red. After it comes to 0, it goes back to red. So if you look at, if you just observe that traffic signal counter and just see what states it goes through, it will be going through this loop again and again and again and again, right, through the entire day. Okay. Now you could program this counter, right, to, you know, the policeman could say, okay, in peak hours I need to give more wait time, so the red will be increased to 120 seconds or the green will also be increased to 60 seconds. So you could do all this, right, but effectively it goes through this state again and again. So of course, you know, there's the color of the counter is green, red, you know, and you know, there is also a display that is actually shown to us, you know, through that red color or green color 7-segment display, right. Now I am not talking about the visual part, I am just talking about the states through which the internal control block of that traffic signal counter you know, goes through, right. So with essentially what we need to do in this course is to be able to model and build such counters, right. For example, an interesting modification to the traffic signal counter would be to skip odd digits, count only even digits, or you may want to count prime numbers, right, or something like that, or you know, multiples of 3, prime number may be hard, but multiples of 3, multiples of 4. How do you do that? Suppose I want the traffic signal to go from 0, 4, 8, 12 and so on. But it should happen after 4 seconds, after 8 seconds. It should not show 1, 2, 3 or 5, 6, 7. These are the interesting kind of circuits that you can build after doing this course, and these are the circuits that you must be able to build after doing this course. And this essentially is called a finite state machine. There are finite states and the system just goes through one by one by one by one after goes through each of these states, and because there are finite states we call it a finite state machine. So while I told you what this course is about, it's also important to know what this course is not about. Okay, so see, lot of logic design courses and all that, even chip design courses and all that talk about automated tool flows. I am not going to talk about a single tool in this course, right, for any purpose, right. It is all going to be pen paper analysis that we are going to do. Okay, so there will be no simulator also that we are going to use in this course. It's all pen paper analysis. The course is not about Verilog design. Most importantly, the course is definitely not about hardware description language based design, right. That is something that you will learn later, and this course is a prerequisite for a Verilog course, right. And it's also not about microprocessor instruction design, right. So this is just to clarify upfront so that your expectations are set right. What are the textbooks? The most common textbook that is used for this course is called Digital Design by Morris Mano and Ciletti, 6th edition, Pearson Education, right. An Indian edition and a paperback version is available. I strongly recommend that all of you please do buy this book and use it for the course. It's a very good textbook in the sense of it has a lot of practice problems, examples worked out. There are lot of things that are, by the way, covered in that textbook. I will point out what chapters I am referring to as and when I do the course. Okay, so I hope you have a good time enjoying this elementary basic logic design course called Digital Systems. See you in the next lecture.